This video is on intermolecular forces. Intermolecular, meaning between molecules. Between molecules. Well, here we're going to refer to the attractive forces between the molecules. It's a little different from a bond. So the example that they're giving us in this section is diatomic hydrogen. And so we're masters of drawing the dot structures. And so we know hydrogen is a really simple dot structure, and hydrogen just has one valence electron, and so with this guy, and we'd usually link them up, and we'd say that they're sharing one single bond or one pair of electrons, and that's great because hydrogen only needs to fill its first energy level, and that only holds 2 electrons anyways. Okay, so this guy right here is a covalent bond. A covalent bond. We could even be more specific and say it's a non-polar covalent bond because those electrons are going to be shared equally. I mean, it's just 2 of the same atom, so they have the same electronegativity, and they would share the electrons to the same extent. So if we wanted to, we could even say non-polar covalent bond, meaning that there's really not going to be a substantial region of charge. The electron pairs shared equally for the most part, and so there's no partial positive or partial negative, or so we think. Okay, so first thing I want to make sure we understand is that thing there, the line in between the 2 hydrogen atoms, that is a bond. Now, bonds involve either sharing electrons or transferring electrons. Bonds can either be ionic or covalent. Bonds are very strong attractive forces between the atoms. Bonding is a good thing. That's how the atoms get their full, stable outer shell, by either transferring or sharing electrons. The bond itself between the atoms is very strong. Here, we're looking at a little bit different force. This is an attractive force between the molecules. So over here in blue, we've got like these bubbly looking hydrogen molecules. We're looking at the attractive force in between the molecules. It's like the molecular glue. It's the glue that holds these hydrogen molecules together. And you can kind of think about it in that the stronger the attraction between the molecules, the more likely they are to maybe be in the solid phase. That if I have a really strong attraction between the molecules, and they're probably going to be held very close together. And if I have the molecules in an arrangement that puts them really close to each other, then they're probably in the solid phase. If we've got weaker attractive forces between the molecules, then they're not held together very strongly, and there's maybe more space in between the molecules, and maybe then they're more likely to be in the gas phase. Okay, so there's a difference between a bond and what we're doing here, an intermolecular force, sometimes referred to as van der Waals forces, but I'll usually call them an intermolecular force, or sometimes I might even abbreviate IMF, and I mean intermolecular force, the attractive force in between the molecules, and it's going to affect the properties of these substances. And one of them would be phase. Okay, so there's a couple different strengths of intermolecular forces. Like there's different strengths of molecular glues. This guy here, this dispersion force, is the weakest. It's the weakest of all intermolecular attractions or intermolecular forces. Sometimes it's just called a dispersion force. Sometimes we refer to it as a London dispersion force after the person that came up with this concept. But here's what happens. First thing that we should make note of is that this type of attraction, this dispersion force, this is for non-polar molecules, or it could be noble gas atoms, or noble gases. So this type of force is going to be really important when we look at nonpolar molecules or just like maybe atoms of a noble gas. Okay, so here's the concept. For example, H2, diatomic hydrogen, was a nonpolar molecule. And so for the most part, these nonpolar molecules do not have substantial charges. The electrons are shared equally, and so 99% of the time, I picture the electrons looking like this. 99% of the time. I think that those two electrons are being shared right smack in the middle of the two hydrogen atoms. If I had like a fancy camera and I could take a picture of the electrons in between the two hydrogen atoms, 99% of the time, they would look like that. They'd be right smack in the middle. However, electrons are always moving within their orbital. And so here what would happen is that the 1s orbital of each hydrogen atom would kind of overlap. They would overlap and they would share that pair of electrons. And so the electrons that are free to move in this region where the orbitals overlap. So what we don't always think about is that if the electrons are moving and their movement is pretty random, what if I could take a picture with my really fancy camera and for a split second in time, whoa, get over there. What if the electron pair looked like this? I mean, this might be like 1% of the time. Do you kind of see what I tried to do there? That I tried to draw the electron pair closer to one hydrogen and not right in the middle. Okay, again, this is not common, but it happens because the electrons are always moving and their movement is random. So because their movement is random, what if for some split second in time, that electron pair just happened to be closer to one hydrogen versus the other? Well, electrons are negative, and so the region that has the electron density, the region where the electrons are, actually becomes partially negative. The region then that's lacking the electrons would become partially positive. But here's the deal. So we just created this region of charge. But this was supposed to be a nonpolar molecule. And nonpolar means that there's no substantial region of charge. Keyword, no substantial region of charge. We can create these temporary charges. This here, that's temporary because the electrons are always moving and their movement is random. And so it's kind of mentioned over here, these London dispersion forces are caused by the motion of electrons, the random motion of electrons. What if by some split second in time, the electrons are closer to one hydrogen than another? Well then, for that moment in time, you will create a temporary region of charge. Okay, so now here's what happens. If I create this temporary region of charge, so now we're kind of looking at maybe this guy. The electrons are moving, and they moved in a way that put the electrons a little bit closer to the hydrogen atom on the right, kind of like my little picture there. And so the right-hand hydrogen got this slightly negative charge, and then the left-hand hydrogen is slightly positive or partially positive. We've seen those little symbols before. Well, now I have a neighboring atom, and I have to picture that, like in the middle here, where we've got this dash, that's really like, whoa. See if I can draw it. Like two electrons being shared. Well, those two electrons are negative, and like charges repel. So if these two hydrogen molecules end up being kind of close to each other, and this region here is a little negative because there's extra electrons in that area, well, in the second hydrogen molecule, then those electrons are going to repel. They're going to say, we don't want to be too close to that negative region, so we're going to repel, and these little electrons are going to go in the opposite direction. They're going to temporarily move away from this partially negative region. Like charges repel. But then do you see what just happened? Check out this picture then. If the electrons in this neighboring molecule are going to move away from that region that was a little negative, you just created another partial charge. Do you see that? Check it out. Down in this guy, then we just created a region where it's going to be slightly negative. If the electrons in that bond are going to move over to the right, well, then that area is going to become partially negative. And then the other hydrogen is going to become partially positive. It's lacking the electrons. Okay, and that was kind of the same thing with my first hydrogen molecule, that this region ended up being a little bit negative just because the electrons were not moving equally between the two hydrogen atoms, and this region became partially positive. What? Like charges repel, opposite charges attract. And so here's what happens. In between these two molecules right in here, here's going to be your area of attraction. Attraction. It's going to be the partially negative region on one molecule and the partially positive region of another molecule. Opposites attract. And so when these two molecules end up being kind of close to each other, they align themselves so that the negative region on one molecule is attracted to the positive region on another molecule. And so now in between those molecules, that's called our London dispersion force, or sometimes it might just be referred to as a dispersion force. I think of it like this. The word dispersion or dispersed, this happens when the electrons are not dispersed equally between the atoms in the molecule. And it's just random and temporary. This is important too. It's temporary. This doesn't last very long because, I mean, think about it. If these electrons move in a way so that they're like kind of close to each other, they're closer to one hydrogen versus the other, just because our movement is random, they don't want to stay like that. Eventually those two electrons are going to repel each other and be like, whoa, we're too close to each other. Let's go back to this. This was kind of our happy place. And the electrons are right smack in the middle of the two hydrogen. But because they move all the time and their movement is random, just by chance, if the electrons are closer to one side of the molecule versus the other, the region of the molecule that is closer to the electrons creates this partial negative charge. If there's another molecule that also has these partial charges, opposites attract. And so the particles will align so that a partial positive is attracted to a partial negative. Opposites attract. But here's why this is weak. It's the weakest of all the attractive forces. It's the weakest because these partial positive and partial negative charges are temporary. This just doesn't last very long. 99% of the time, we might not have any attractive forces because 99% of the time, those two hydrogen atoms will share the electrons equally. Oh, interesting. And so here's the other thing that we should mention. If I had, let's say I have a couple atoms. Let's do some noble gas atoms. So maybe helium versus krypton. Helium versus krypton. Okay, so helium is a pretty small atom, and we'll give it a positive nucleus in the middle. And krypton's a pretty big atom. 1, 2, 3, 4 energy levels. I'll just make it really big. And then here's the positive nucleus. Okay, so when I think about the electrons in helium, there's only two. And so if there's only two electrons, and obviously like charges repel, for the most part, those two electrons will probably be like opposite each other around the nucleus. You know, they're sharing the 1s orbital. They're going to repel and they're going to orient themselves for the most part on opposite ends of the molecule. Or I should say on the atom. Now, could they move? Of course. I mean, this is maybe like 99% of the time. They're going to repel each other in the 1s orbital, and they'll be as far apart as they possibly can be. But here might be the other 1% of the time. And so it's possible that those electrons are just moving around, they're having a good time, and whoa, sorry, we're in the same place at the same time. Well, then the region of the atom that's got the electrons creates this partially negative charge, and the region of the atom that's lacking the electrons becomes partially positive. But that's temporary. We want to go back to that 99% as soon as possible. Because again, these dots represent negative electrons and like charges repel. Well, now think about krypton. Krypton's got 36 electrons. That's a lot of electrons. And they're moving amongst lots of different orbitals. And so here's what kind of happens over time. Let's say I got 36 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. I think it's 36. It's somewhere in there, right? Okay, do you kind of see what I drew here? That one area of the atom definitely has more electrons. You know, this area seems to have more electrons, so that area is going to be slightly negative. And then the opposite end of the atom that's kind of lacking the electrons will be slightly positive, partially positive. So here's the thing that I wanted to show you, that these are both noble gas atoms. And this would be the same for a nonpolar molecule. Nonpolar molecules and noble gas atoms don't have substantial regions of charge. The only way they can create a charge is this, by just the random movement of electrons. But the more electrons you have, the harder it is to keep them evenly spaced in all their orbitals. There's 36 electrons distributed amongst tons of orbitals. And so there's just a greater chance that their movement is random and that all it takes is a few electrons to sway one way or another, and you're going to create a partial region of charge. When I only have 2 electrons in one orbital, it's pretty likely that they're going to stay away from each other. I was thinking about, like, if you were going on a field trip with 2 kindergartners. Well, you got one on each hand, and you can keep them organized and away from each other. You can keep those 2 toddlers in a pretty equal distribution if you were like the center. Well, now let's say I'm going on a field trip and I'm taking 36 kindergartners. That's mass chaos. 36 kindergartners, what are the chances that they're all going to be like in their space at the same time and they're all waiting in line just perfectly? No, they're all moving around like crazy. Now, that kind of reminds me of like krypton, where it's just harder to keep more electrons evenly distributed amongst lots of orbitals. So the more electrons you have, the greater the chance that they'll create these temporary regions of charge, which then would create attractive forces in between the atoms.